Hello. Yeah. Today we have another data learning seminar. So welcome everyone. Today we have Shuo Wang, a former colleague at the Data Science Institute at Imperial College, and now currently working in the Digital Medicine Research Center in Fudan, China. Shuo, I'll leave the audience with you.
Okay.
Yeah. Go ahead.
Thank you, Cesar. Thank you for inviting me. So today I'm very glad to give a talk about my research on cardiac image analysis. So I have worked in Data Science Institute for 2 years, working very close to Wenjia and Ike. Now I'm based in China and started my new job in Fudan University since March. And today I will review some work we have done before using generative models, in particular on the application to the quality control and the super resolution for cardiac segmentations. Here is the content I will talk about today. I aim to finish in 15 minutes and I will leave some time for questions. First, I will give some brief introduction on the cardiac imaging background and some challenges in clinical practice. Next, I will introduce the framework we established based on generative models and the latent space exploration. The framework is applied to cardiac segmentation for two purposes. The first one is to detect the bad segmentations generated by AI models. The second one is to enhance the cardiac segmentations by joint super resolution and motion correction. Finally, I will talk a little bit about the population imaging study, the UK Biobank we have worked on. That is the Smart Heart project. Okay, as we know, heart is one of the most important organs in our body. It is responsible for pumping the fresh blood to the brain, stomach, legs, and all the rest parts. Yeah, I don't know whether you can see my face with cardiac models.
You can see it.
Yeah, so let's take a close look at the cardiac region. So it's composed of two ventricles, the left ventricle and the right ventricle, and two atriums, the left atrium and the right atrium. They work together to drain the blood from the wing and deliver the blood into the aorta. During a cardiac cycle as shown here, the heart contracts and relax regularly to maintain the pumping power. So we should thank our hearts indeed. They work 24 hours every day and night. Sadly, there are a number of types of heart disease with multiple causes. Many times, a process called atherosclerosis is part of the problem. Atherosclerosis happens when a fatty material builds up on the coronary arteries and occluding the blood perfusion to cardiac muscles. It can cause symptoms like heart attack and chest pain. The next one is cardiomyopathy. Cardiomyopathy is a type of heart disease that can cause muscle tissue to become weak, making it harder for the heart to pump blood to the aorta. Cardiomyopathy may cause heart failure. On the left is pericarditis. A thin layer of tissue called pericardium surrounds our heart. Its job is to hold our heart in the place and help it work properly. Pericarditis happens when the pericardium becomes inflamed or swollen. This condition can be acute or chronic. Untreated pericarditis can lead to heart failure. There are also several other types of cardiac disease. Okay, how do we evaluate our cardiac function and make clinical diagnosis? We have the cardiac imaging to help us. In clinical practice, doctors use ultrasound, CT, MRI to image the cardiac structures and evaluate their functions, such as the ventricles, the coronary arteries, and the valves. Now, cardiac MRI is the gold standard modality to evaluate the cardiac functions. The most used cardiac MRI is called cine. So it's like a video of our beating heart during one cardiac cycle, as shown here. So although 3D MRI is available in research setting, it needs to hold a very long breath. that is not realistic for patients. So therefore, in clinical practice, 2D CT scans are the most used ones. We hold our breath and one slice is acquired. Because the heart is in 3D structure, different slice views can be used. Typically, two kinds of views. One is called the short axis view, one is called the long axis views can be acquired. The long axis view can include the 4-chamber view and 2-chamber views, as shown in the purple plane and the blue plane here. So usually in clinical settings, we acquired a stack of short axis views plus 2 complementary long axis views. Like here, we have a stack of short axis views and 2 individual long axis views. Now let's look at how we analyze the cardiac images. The segmentation is the first step. For a given cardiac image, we need to recognize the cardiac structure and classify the pixels into their categories. Does this pixel belong to the left ventricle, myocardium, or right ventricle? This is the process called medical image segmentation. Then we can perform the quantitative analysis based on the segmentation results. Before machine learning is popular, we rely on the doctors to annotate the cardiac structures manually. This is time-consuming and expensive. With machine learning, we can develop automatic segmentation models. For example, shown here, in early years, we can split the image into patches and use the random forest to make the prediction. With the deep neural network, we have the Fourier convolutional neural network called FCN, or we have the famous UNet to perform the end-to-end segmentation. This has achieved segmentation accuracy comparable to medical experts. In our group, we also tried to improve the data efficiency by using the dynamic system to mimic the human annotating, achieving very good results. However, no matter what kind of segmentation models we are using, either random forest, FCN, UNet, or other segmentation models, even we get very good results in labs, when we deploy them to unseen dataset or real clinical dataset, it is inevitable to generate some poor segmentations because of the image noise or motion artifacts or other domain shift issues, as shown in this picture. Before we use the segmentations for clinical assessment, it is essential to do the step called quality control. The aim of quality control is to identify the poor segmentations for further check and correction. Of course, we can ask doctors to do manually quality control. However, when we are dealing with the big data from clinical practice, a reliable and automated quality control method is much more desired. The problem of quality control is often formulated as a prediction task. Given an image and test segmentation, the task is to predict the quality score, such a dice score between the test segmentation and the ground truth segmentation. The challenge here is that the ground truth segmentation is unknown. So how do we do the quality control? Existing measures for quality control for medical image segmentation can be summarized in 2 ways. The first way is called the regression base. So the task here is to learn a function f to do the regression task, to regress the quality score based on the image features and also the segmentation features. For example, hand-correlative features have been proposed, and the CNN-based methods also proposed to learn features for quality control end-to-end. However, the regression-based methods require a training set, including both good quality and poor quality segmentation as supervision. This makes the quality control specific to some certain segmentation models. As we know, good segmentations are all alike. Every bad segmentation is bad in its own way. So the limitation of this method is that we cannot create a perfect training data set with every bad segmentation included. The other direction is to use registration methods. First, we can curate a subset of representative image and their ground truth segmentations as a reference data set. Then for a given segmentation and image, we can do the registration between images, and we use the registration transformation to warp the reference segmentation. Then we can compare the warped segmentation with our test segmentation. Then we can calculate the quality metric. Along this direction, ICA methods was proposed and successfully applied to the quality control for large cardiac MR datasets. However, this method is computationally expensive due to requirement of the image registration. So in our work, we propose a generative model-based quality control framework. So the motivation here is because the ground truth segmentation is not available. Can we find a surrogate segmentation to replace the ground truth segmentation to do the calculation of quality score? So we have two assumptions. First, we assume that good quality segmentations live on a manifold in the whole high-dimensional segmentation space in the surface called sigma. Then the second assumption is that for given test segmentations, we can find a surrogate segmentations on the manifold for the purpose of quality control. Then we can calculate the distance of the similarity metric between these two. Then how we find the surrogate segmentations on the manifold? We do this through the generative model. First step is to learn the good quality data manifold using a generative model. After that, for arbitrary coordinates in the latent space of the generative model, it can be mapped to a plausible segmentation on the good quality manifold. The next step is the iterative search in the latent space. The aim is to find the closest surrogate segmentations on the manifold to the test segmentation. Then it is used to calculate the quality metric. The advantage of our proposed framework are here. First, because we only need the ground truth images and segmentations to learn the manifold, our method is independent of the segmentation model. That means our method can be used for any segmentation model, such as random forest, FCN, or UNet. It is also independent of different types of segmentation failures. Our framework is compatible to different generative models, including variational autoencoders, and again, other advanced architectures combining these two. As long as a smooth latent space is available for the latent exploration, the iterative search can be performed and the quality control can be also performed. Moreover, the iterative search in the latent space is guided by the gradient backpropagate through the generative model. This can be accelerated with GPUs for real-time evaluation. So here we show the simple implementation of our proposed framework using a VE. So the network is a standard VE with a convolutional encoder and decoder. The encoder includes 4 convolution layers with strided convolution and ReLU activation. The decoder includes 4 transposed convolution layers and ReLU activation as well. The input is a pair of 2D cardiac MR image and the corresponding test segmentations. They are encoded to the latent coordinates by the encoder, then reconstructed through the decoder. The framework includes 2 stages. First is the training stage. Only ground truth segmentations are used to train the VE to learn a generative model representing the good quality manifold. The parameters of the encoder and decoders are optimized with respect to the AVE loss. For the application stage, after the generative model, which is the decoder here, is well trained, we freeze the weights and giving a test segmentation, we combine it with the image as the input as the encoder and get an initial coordinate in the latent space. Then we iteratively update the latent coordinates to optimize the difference between the surrogate, the generative surrogate segmentation and the test segmentation. After convergence, the final surrogate is used to approximate the quality score, such as the dice score. So here we show some visualization of this framework to gain more insights. We trained WAE with 2 dimensions for visualization purpose here. On the right is a random case in the application stage. This is the image, and this is the ground truth segmentation of the image. And this test segmentation is in good quality due to image artifacts. First, the WAE encoder provides an initial latent coordinates here, as shown in green points here. This is a starting point for the iterative search. The reconstructed surrogate segmentation is visualized here. Then the trajectories of the optimization process in the latent space is visualized. And the surrogate segmentation after 100 iterations is visualized here. This surrogate segmentation looks plausible while it keeps the similarity with the test segmentation. With more iterations, the surrogate segmentation is further optimized and looks more similar to the ground truth. Finding the quality score can be calculated between the test segmentation and the surrogate segmentation. We further visualize another 5 random cases during the application. This includes different slices of the short axis, such as the basal slice, the mid-ventricle slices, and the apical slice. We observe that all surrogate segmentation are plausible, close to the ground truth. We perform several experiments to verify the effectiveness of our proposed method. The first experiment evaluates the simulated segmentation failures due to image noise. We use the cardiac MRI image from UK Biobank dataset. They are short axis SSFP CNE scans, and the ground truth segmentations are available. In total, 1,500 subjects are used. These data are divided into train validation and test dataset on subject level. The segmentation network is a FCN which has been validated to produce expert level segmentations of myocardium. First, we use the ground truth segmentation to train our generative model for quality control purpose. Then we add Gaussian noise to the images to fool segmentation models and produce pool segmentations. Then we use our quality control model to evaluate the quality. The evaluation is performed by comparing the predict dice score to the real dice score. We calculate the Pearson coefficient R and the mean absolute error MAE among the test dataset of the 500 test subjects. For comparison, we also implemented 2 regression-based methods. One is on the handcrafted features, and one is on the CNN regression-based, which is considered as a SOTA method. The axis is in this plot is the real dice score, and the y-axis is the predict dice score. The dashed line is y equal x. The quality control method is best if the scatter points distribute around the dashed line. The results here show that our proposed method outperforms handcrafted features models and achieve comparable performance to the state-of-the-art CNN regression, while we only use the ground truth segmentations for training. Then we perform an experiment mimicking the real-world deployment of a well-trained segmentation model. We use the ACDC datasets, including also the CNE cardiac MR scans, but with different spacings. The UK Biobank dataset includes most healthy volunteers, but this ACDC dataset includes for different kinds of pathologies and come from different machines, including 1.5 Tesla and 3 Tesla MR scanners. We deploy the pre-trained FCN segmentation models onto the ACDT dataset without fine-tuning. It will result some segmentations with poor qualities. This simulates the scenario that we deploy a well-trained segmentation model to the real clinical practice. We use our quality control method to evaluate the segmentation performance on ACDC dataset. So we show our results here. We observe that for the regression-based method, both the handcrafted features and the Bayesian regression, they show a clear deviation from the identity line. This demonstrates the failure of quality control due to domain shift issues. The 5 different colors represent subjects with one normal group and other 4 different pathology groups. In contrast with the regression-based methods, our generative model-based quality control show excellent performance in terms of quality score prediction. The performance is consistent well among all the 5 different subgroups. So here I will show some quantitative evaluation results of these 2 experiments. We confirm the satisfactory performance of our proposed methods. On the training domain, our proposed methods achieved a similar performance to the SOTA-Bayesian regression method. Our results show better generalization abilities with excellent performance on unseen domains on ACDC. This demonstrates the advantage of our proposed framework and shows the potential for the real clinical practice use. So, in brief, we propose a generative model-based framework for the quality control of segmentation, which is compatible to different generative models and show better generalization abilities than descriptive models, and is segmentation model agnostic. And can we go one step further, as we have identified some bad segmentations? Can we repair the bad segmentations according to the manifold prior? Can we also enhance the segmentations to 3D reconstruction? So that's the next part I will introduce. So first, let's look back to the 2D scans of the cardiac MI. So although I have talked about that the clinical MI include a stacks of short axis views. They are scanned slice by slice. The problem is like the gap between the 2 slices is large compared to the in-plane resolution. So although we have the 2D segmentation slice by slice, because of the large gap, it is difficult to reconstruct high-quality 3D models. So for example, so this is the ideal data set we want to acquire. That is, this is acquired from 3D sequence in research setting. That means the resolution in both in-plane and out-plane are both high resolution here. So in XY plane, the short axis is high resolution. In long axis, which is XZ plane, is also high resolution. We can create some good 3D representation, such as the surface from the volume. But in real clinical scenarios, what we have is this clinical scan, which is slice by slice 2D scan. So this results in the low resolution in the XZ plane because of the gap between 2 slices. And if we generate the 3D models, 3D surface from the volume, we will have the staircase artifacts. So how can we improve the resolution along the zeta axis and also reduce some artifacts? That's a problem we want to solve. Besides the low resolution, there is another problem called respiratory motion. That's the interslice displacements caused by our breath. Because each slice is acquired when we hold our breath. When we hold our breath for several times, the several slices were acquired. There may be some motion interslice. So on the left shows some normal motion. On the right shows some like bad motions. It's some severe motion. Maybe it's a patient who cannot hold their breath properly and cause the interslice displacement large. So in general, we have different types of segmentation degradations, such as the low resolution along the z-axis and the motion shift because of the breath holding. And sometimes we also get some topological defect, like a missing slice. This can be happen like when we have one slice with bad quality, with very bad noise, and we cannot get useful segmentations from that slice. So we face the missing slice. And how can we use our generative model-based framework to repair these bad segmentations or the degraded segmentations, to perform the joint motion correction and the super-resolution to get the high-resolution segmentations? So let's look at the related work first. So here, from the review, I copied some demonstrations of the state-of-the-art super-resolution network. Both are the supervised learning. That means the input is a low-resolution image, the output is a high-resolution image. And the network is trained in a supervised way. That means you have the paired image with both low resolution and high resolution. In our framework, we use a similar framework as we developed for quality control. The first stage is to learn the high resolutional manifold of the segmentations. That means we learn a generative models. Like for an arbitrary coordinates in the latent space, we can map the latent space coordinates to a good quality segmentation, which is high resolution without motion and without topological defects. So what we need is a data set of a ground truth or the good quality HR data set, the high resolution data set. So after we have a generative model well trained, we can start the latent optimization as well. So it's similar to the previous quality control framework. We can draw an arbitrary points in the latent space as the initial guess. Then with the generative model, we can have a super resolution candidate. Then we do the downsampling motion, adding some motion through the differentiable layer. Then we have the degradation results. We can compare the candidate results with the input. So the input here is the short x stacks. Then we can calculate the similarity or the loss, and we can backpropagate to the latent space, then to iterate in the latent space until we find the best candidate super resolution results, which is the results we want to get. And besides the short access, as we said, like we have some long access views as well. So one advantage of this framework is like we can easily add the multi-view capacity to this. For example, if you have the long access views, we can have one branch, so we can slice your generated segmentations, and we can have the projected segmentation and compare to the inputs long access view. And we can calculate the loss on both long access view and the short access views. Then we can have the total loss and backpropagate to the latent space to the joint optimization of the zeta and the d together. So before we show some results, we want to demonstrate like the upbound of our generative model performance. That means for giving you ground truth segmentations, so how likely you can recover itself through your framework. So we test some ground truth segmentations and we do statistics. We find like the LV here is called the left ventricle, is the green color here. Myocardium is the yellow here, and the right ventricle is the blue here. We have the upper bound is like all above 0.95. And the second row is the inter-observer similarity. That means for one image, two different radiologists or doctors draw the segmentations and what's their similarity. We can say like our outbound go beyond the inter-observer similarity. That means our method is in theory like is suitable for this kind of job of super resolution. So, okay, first we do some benchmarking things on simulated degradations. We have a data set of a high resolution data set. Then we perform 3 different types of 3 degradation patterns onto the data set. Then we get 3 different paired data set with a high resolution data set with no motion, normal motion, and severe motion. And we have some baseline models. The first is upsampling models, which is a very baseline with the nearest neighbor. And the second one is a shape-based interpolation, which considers the local shape to do the upsampling, but not learning-based. The third one is like one of the SOTA methods for image super resolution called enhanced deep residue network called ADSR as a deep learning based super resolution CNN. So because for training such a supervised learning method, we need the paired data set. So we trained on one domain and test on the same domain for the EDSR model. For our LO, which means the latent optimization framework, we don't need the paired trained data. So we just test on all the three domains without further training. And we can observe like our proposed results matched the EDSR performance in their individual domains and outperform all the simple or traditional interpolation or upsampling methods. And in particular, under the severe motion patterns, our results beat all the other three methods. And our upper bound, as we shown, like the limit of our performance is shown here for comparison. It shows like our proposed methods hasn't reached the upper bound, means like we still have some space to improve the generative model or the optimization technique. Here is some visualization of the results. So the first, the top row is about the normal motion. Yeah, it's like the motion, the interslice displacement is not large. And the bottom column is the severe motion. We can say the interslice displacement is rather large. And on the right is the ground truth. And for the normal motion, our results and the EDSR, the supervised learning-based methods perform equally well. We can see here. But for the severe motion, we can say our results is quite robust compared to the EDSR here, and much better than the shape-based or the nearest neighbor upsampling methods. So compared to the EDSR models, which is supervised learning, we compare the cross-domain generalization abilities. As we introduced, we have the high resolution data set, and we simulate some different domains with a no motion, a normal motion, and severe motion. For the EDSR, we need to train 3 different models to represent the mapping here, and for the super resolution mapping. And when we applied one model trained on a certain domain and applied to another domain, the results will be not good, as we shown here. If we train on the same domain and test on the same domain, the results of EDSR is okay. But when you apply to another domain, so the results, the performance dropped largely if the degradation patterns is different. So under these scenarios, our latent optimization methods outperform the EDSR models by a large margin here. This also reminds us that for supervised super resolution, the training data set should be carefully prepared, reflecting the real data distribution to be deployed. So here we also show the advantage of our framework to keep the anatomical plausibilities. So here on the left is an example of in the real clinical practice for the scan of the stack of 2D scans. We can see some like large noise in the middle slice, and this will cause the missing slice in the 3D stack. And if we use this missing slices segmentation as the input to the NN, SBI, or EDSR, we will get these results. It's interesting to say like the EDSR model try to close the bottom of the upper part of the topological defects. So he thinks that's he want to refine the segmentation into two small halves. So that means it's learning some like local features. But our proposed framework keeps the topological like plausible, like it's always a good segmentation in terms of the topology connectivities and the resolutions. So besides the imaging technique and the AI analysis, so I will introduce some other work on the populational imaging studies. So maybe you know, like the UK Biobank, we have a large cohort with their image data, also the genomics, also the clinical record. And what we can do is like we can extract the quantitative phenotypes from the cardiac imagings, like the volume of the left ventricle, like the cardiac functions. Then we can correlate these phenotypes to the genomics, other habitats, like and other some like clinical things, like sports, intelligence, also maybe persuade different kinds of the factors. And we can use data mining to find the correlated things. So here is a Manhattan plot of the correlations we discovered. This was mainly done by Wen Jia and published in Nature Medicine last year. So we found like the cardiac functions is closely correlated with some like the physical measures, lifestyles, and interestingly, it's also linked to the cognitive function. That means the cardiac region and your brain region are closely connected. And we also find some like novel correlations, and we also did some like causal inference as well to confirm that the correlation is causal. That's all the things I presented today. I want to thank my colleagues in Imperial College and the founding bodies. So thank you. So any question is welcome.
Thank you, Shuo. Yeah, you have any questions for Shuo about his amazing work he has done and he presented just now? Just write it in the chat and I can read it out for you, or you can ask it directly to him.
Yes, thank you, Shuo, for the nice presentation. I have a question. Is that when you deal with the three-dimensional objects, so you make slices in order to transform that into two-dimensional images. So I wonder if there is an optimal position to make these slices, or maybe you can consider that as a hyperparameters in your model, or maybe the positions are fixed. How is that in the? Yeah.
Okay, so let's look at this cardiac model here. So can you see the cardiac model? So for the IMR scanning, so I cannot choose which slice to scan. That's because the IMR physicist will do that. So they will choose this is the long axis, this is z-axis, and this is the short axis view. So they will scan this direction slice by slice. So what we will get is this short axis images as a stack. And what I deal with is the 2D slices in these directions. And we do the super resolution and the quality control with these 2D slices.
Okay, I see. So the positions are already given, right?
Yes. And we can read that from the medical imagery header files from the DICOM header to determine the 3D orientation of the plane.
Okay, thank you.
I can see Claire, you have a question?
Hi, thanks, Caesar. Thanks, Shuo, for that presentation. That was really interesting. We've been doing something a bit similar to your latent space exploration to try to get generative adversarial networks to predict in time. So we've been trying to search a latent space to find a variable that coincides with a certain set of time series values, so we can make predictions. I wondered if you'd found or had any problems during that optimization process or that exploration of the latent space. Do you ever get stuck in certain positions or unable to get to a place that well matches your ground truth or your test solution?
Yeah, thank you. It's a very good question about the optimization technique we need to consider. So I will show with my slides. For example, so here I showed like in the 2D dimension, so the search can converge easily. But when when we did the super resolution search, like which is actually 64 dimensions, so it's indeed searching in a high dimensional space. So we need to be careful, like to be stuck with some local minima. So what we did is like we use multiple starting points, and we will keep the best ones. So we are still working on developing some more robust optimization technique to guarantee or to confirm like we reach the good convergence to the good points.
Great, yeah, that's really interesting. Thanks, Shuo.
Thank you.
Yeah, I was gonna say that look similar to the backpropagation that you were working with, Vinicius.
Yeah, the Predgan, yeah.
We also have sorry, I didn't look at the order. Maybe Isaac first and then Amir.
Yeah, hi. I wanted to ask a quick question about if the quality control metric that you're getting from this process of training the surrogate model, if that is something that tells you about the kind of quality of the segmentation, whether that could be used as part of, if the segmentation model is already trained, if that could be maybe part of like a retraining process and incorporated into like the loss function to try and minimize that mismatch between the
So it's also a very good question. So actually some people already did that. So what they did, they add autoencoder at the end of the segmentation as a post-processing, like they learned the autoencoder with good segmentations and using that loss incorporate to the total loss, then to improve the segmentation model. For here, so our purpose is a little different because we are doing the quality control. It's like we want to predict the qualities, and maybe the power, like the prediction power, maybe that fine enough to improve the segmentations. But it's totally doable because for the super resolution, what we did is to improve the 3D segmentation, like from the bad segmentation to good segmentations.
Yeah. Thanks.
Thank you.
We also have Amir.
Yes. Hi, Shuo. Thank you for the talk. I also have a question about the latent space exploration. So when you're trying to find a structure to generate, and maybe while doing the exploration, you are going further away from normal distribution and from like probabilities that you never really encountered while generating structures. So maybe the generator is not generating real looking structures. So how do you deal with it? And did you encounter it?
Yeah, that's a good question. So that's like kind of the creativity of the alternative model and or the diversity of the alternative models. That's the reason why we did some quick test on the upper bound of the performance. That means I give you like a realistic segmentations, can you reconstruct that, or you can find that in the latent space? So in our real world test, so our results show like, okay, for the almost every normal cardiac segmentations, we can find the matching points in the latent space. Another question is like, when you search in the latent space, will you meet some like points that generate some bad segmentations? The answer is yes. If your generative model is not good enough, so you will have some, for example, your latent space is not very smooth. You will have some holes in the manifold. So how to avoid that is we use the beta VE. We adjust the beta, which is the regularization weight. Like we want the latent space to be like very smooth and continuous. I will show you some like ablation studies. We tried different ways of the loss as an ablation study and find the best combination of the different loss to get good enough generation models to do the task. For the beta VE, if we set the beta as 0, so that's an autoencoder. If we set the beta a large value, that means we impose a very strict requirement of the smooth latent space. So we need to take a trade-off between these two. And what our solution is like, we use some like grid search to find the best one.
Thank you.
Okay.
Thank you, Amir. Isaac, you have another question?
Oh, sorry, I just forgot to take my hand down.
Okay, cool. Yeah, no worries. I have a question, Shuo. Yeah, so in the application of, so these are cardiac applications. Could it be possible is your workflow like general enough to apply it to maybe a different organ, for example, let's say lungs?
Yeah, so let's go back to our assumptions. So the options, so actually our assumption is based on we think the good segmentations or the target segmentations are distributed on a manifold. So actually the evidence for that is like, we all know like our organs has its own structures, like the heart structures, the lung structures, they have different structures. But as long as it's physiological, it should follow some like similar shapes. So let's give you the confidence, like you can learn the good quality, can learn the manifold. So my answer to your question is like, for some normal organs, for organs, I think it's no problem. But for some tumors, maybe tumors, you have like different shapes. So these measures will be kind of difficult, because for quality control, you don't know what's the shape for the quality control of the tumor segmentation. Maybe the bottleneck is not about the shape, it's about the boundary, like the contrast, whether this contour like have the most contrast between the inner tumor and outer tumor. So I think this framework is more suitable for some organ segmentations rather than some like tumor things.
Okay. And my other question was like, how long will it take to like train one of these models, specifically the super resolution one? Is it quite computationally expensive?
So actually, I will show the structure here. So okay, on the top is the beta VE we used as our generative models. So it's, if you look at the details, it's not that large. So we only train that with one single GPU is enough, because we are dealing with segmentation. It's not images. So what we have is one-hot encoding of 4 channels, because we have 4 different components.
Okay.
And then we use a simple beta VE to do that job. And for training is within like several hours. So for 200 epochs for the thousands of segmentations, the ground truth segmentation, we have 2000. So it's not a heavy training task.
Okay. Yeah, anyone else? Thank you, Shuo. Anyone else have another question?
Yeah, thank you. If you have any question, you can drop me an email. So I will try to answer you. Yeah.
Yep. Well, in that case, if no one else has any more questions, we can just stop the meeting here, and we can thank Shuo for his presentation. I know it's very late in China, so we'll let you go to sleep.
Yeah. Thank you, Cesar. Thank you, everyone. See you. Bye.
Yeah. Thank you, everyone.
Thanks, Shuo. Bye, everyone.
Bye-bye.
Bye.
Thank you. Bye.